Today, with deep learning technologies, we have the possibility to solve new and difficult problems. For these problems with rule-based algorithms, we didn't even know where to start with a few years ago. For deep learning-based object detection, this is clear. The first step in our workflow is to label the data. And this labeling process can be time-consuming and sometimes also annoying. So in this talk, I will give you some insights how to reduce the label effort and also keep the good precision of our deep learning-based technologies. To be all on the same page, let's consider this image. In this image, we want to find all the different types of screws and localize them with oriented bounding boxes, as shown here. So this is a result of a supervised setting where we have labeled 400 images and over 4,000 instances of the screws. So this took approximately 1 week. So the first question that comes into our mind is, how can we reduce this label effort? And if we have reduced the label effort, can we still keep the good precision of our model? And another question that our product manager usually asks is, what are the implications for the runtime? So let's start to reduce the label effort. For this, we use some of the tools that we have within HALCON. And to start very easy, we take a plain, homogeneous, white background. On this background, we can now put our screws, our objects. And if we subtract the background and apply a thresholding on this difference image, then we can obtain the region, the approximate region of the screw. This can be refined with another operator, closing circle, to close the holes inside the region. And now that we have this region, we can continue to infer the bounding box and also the orientation of the object. This can be done not only for one object, but for all the types of screws and nuts that we have in our dataset. By this, we have obtained a so-called weakly supervised setting, because we only had to annotate the class, and that was really easy because we know which type of object we have put on the background. And the box has been inferred by HALCON automatically, more or less. So now we are not quite there yet, because with this white background images, we cannot train our model and assume that we will succeed in this wooden background with many different types of screws on it. So the second step is to generate images that look more similar to our test setting. For this, again, we take an empty background, but this time a wooden background similar to the one that we have in our test images. Also here, we now put the objects onto it, but this is done artificially. We crop them from our template images, the white ones, and we paste them onto the wooden background. And this can not only be done once, but randomly with random numbers of objects, with random positions, orientations, and classes. The good thing is that we can remember where we pasted them, and so we also have the regions. From the regions, again, we can infer the bounding box and the orientation. What we get is fully annotated, generated images. They might look a bit artificial, but the good thing is we cannot do this only once, but several times, 1,000 times, 6,000 times, or 10,000 times, and we just have to wait a few hours maybe until our processing is done. With this, we have generated artificial training images using HALCON. We have now a large training set, and we are ready to train our deep learning-based object detection model. The training is done exactly in the same manner as it's done for the supervised setting, so we don't have to show you this. So let's just skip the training part and look at the results. If we have a first look, we can be really impressed by the results, even considering that we only annotated the classes of the 13 different screws. But if we look more closely, we find some failure cases. For example, sometimes the class is wrong, or we have some false positives. Maybe along the thread of another screw, it's found duplicates, or we have false positives in the background. If we look more closely, we also find that sometimes the results are not quite precise. Here, for example, the box is too small, and here in this other example, we have to look really carefully to obtain that the orientation is not exactly parallel to the thread of the screw. Okay, let's also have a look at quantitative numbers, comparing this setting with the weakly supervised labels to the fully supervised. For this, we look at different measures. One is the mean average precision. It summarizes the whole detection performance in one single number. But we also look at the number of true positives and the number of false positives, because these are sometimes a little bit strangely incorporated into the mean average precision, and they are also interesting. And we have a look at the runtime. So first, our baseline is the manually labeled dataset, these 400 images with over 4,000 hand-labeled boxes. If we look at the lightweight backbone, the compact backbone, then we achieve an MAP of 86%, and there are still some numbers of false positives, but the runtime is pretty fast. We can improve this result using a heavier ResNet 50 backbone and improve the mean average precision and also reduce the number of false positives. However, the model gets a little bit slower. So now we can do exactly the same thing with our weakly supervised data that was used for training and validation. If we generate 6,000 images exactly in the way as I've shown you before and use the compact backbone, we are pretty close to the result that we had in the supervised setting. And of course, also here we can use the heavier ResNet backbone and even obtain a result that is better than in this fully supervised setting. The runtimes, of course, are approximately similar to the ones in the fully supervised setting. As you see, there are still some rows left in this table. So if we see deep learning as only one possibility that we have inside our HALCON toolbox, we could also look into our toolbox again and see if there's something else. For example, in this application, shape-based matching is a good choice that also works well. For this, also here we can use the template images to have a fair comparison. So we use the white background template images and we create the shape models on these template images. So one shape model for each screw type. When we are done, we are immediately ready to apply the shape models on our test image. For this, we just have to call find shape models. However, we have to keep in mind that the shape model, as the name already suggests, is looking at the shape, so the edges of the objects. In our dataset, we have two different kind of screws that look really similar concerning the shape, and the difference is only their color. So here we need a little post-processing to look at the color at the center of the screw. If the color is dark, we choose the one type. If it's light, we choose the other one. So now we are already ready to apply the model, and if we look at the results, the first impression is the results are really precise, and mostly the correct objects are found. However, it's not difficult to see that also here we have some failure cases. There are many different false positives, sometimes duplicate detections along the thread of the screw with opposite orientation, or some false positives in the background. And especially we found that for the small screw, which is shown in red, the shape-based matching has some difficulties. Okay, looking at this quantitatively, we see that the MAP is even improved from our best deep learning-based model. This is because the true positives are so precise and they have a high score compared to the false positives. But the number of false positives is a lot higher than for the deep learning-based case. So now we have seen two different approaches to solve this task. And why not combine them in a hybrid approach? HALCON is the perfect solution to do this in one framework. So let's start with a deep learning model, just the one that we have seen before. So we see the same results as in the weakly supervised setting that we have seen before. So now we use these results to restrict the search space of shape-based matching. More precisely, we only apply fine shape models at the center or around the center of the screws that we have found with deep learning. And therefore, we can restrict the orientation, and also we don't have to search all over the whole image for each type of the screw. However, we have to be careful here, because if this deep learning-based model is wrong, we cannot find the screw with shape-based matching. So what we do is that we always look for similar screws. If the deep learning-based model found a large screw, we apply fine shape models for all types of large screws. If a medium-sized screw is found, we find the shape model for all medium-sized screws. And finally, we don't need to search again for the results that are precisely found by deep learning. For example, the nut categories are typically found very precisely by deep learning. And we have also seen that shape-based matching has some difficulties with the small screws. So here we just take the result from the deep learning-based object detection. So what remains is just that we can enjoy the results on our test images. Maybe you have remembered one or two of the failure cases that we have seen before, and all of them are now gone. Of course, this also reflects in the quantitative analysis. We now have a really high number of true positives, we have a really high MAP, and we have a really low number of false positives. What is also interesting is that we could reduce the runtime of shape-based matching almost by a factor of 10 and end up with a runtime that is real-time capable. So let's come back to the questions that we raised in the beginning. The first was, how can we reduce the labeling effort? And the answer was that we can use a weak supervision and data generation to generate large data sets with HALCON. The second question was that if we reduce the labeling effort, how can we keep the good precision? And I think we have to rephrase this question. The question should be rather, how can we improve the good precision? And the answer was here that we can use in HALCON a hybrid model using first deep learning and then together with shape-based matching achieve the best possible result. And finally, I can answer the question of our product manager and tell him that our model is really fast. So this concludes my talk. Thanks for watching. I hope you have gained some insights how to combine different tools within the HALCON toolbox to achieve your goals.